In this presentation, we will examine the basic types of rotary optical encoders, examine the basic types of rotary magnetic encoders, understand resolution, accuracy, and repeatability of encoders, examine some different mounting options, look at encoder wiring and grounding. A rotary encoder is a type of position sensor which is used to determine the angular position of a rotating shaft. It generates an electrical signal, either analog or digital, which indicates the rotational movement of the shaft for accurate speed and position control. The two most common types of rotary encoder are incremental, also known as quadrature, and absolute. For industrial applications, incremental encoders are typically used with AC induction motors when only the relative position is needed. Absolute encoders are often paired with servo motors, as this gives a different binary output at each position so that the shaft position is absolutely determined. Multi-turn encoders can continue tracking changes over multiple 360-degree turns by using extra discs to count complete revolutions which are driven by internal gears. Rotary optical encoders are the most common design. This type consists of an LED light source, a light detector, a code disc, and a signal processor. The disc has opaque and transparent segments and rotates between the LED and the detector to intermittently interrupt the light beam. The detector tracks the number of light exposures it receives and sends that information to the processor. An incremental encoder's output consists of two square waves, each of which correspond to an increment of rotation. Two light beams pass through the disc onto the photodiode. Light beams A and B are each received by a separate diode and converted into two square wave signals at 90 degrees out of phase, known as quadrature output. This output will then determine the speed, direction, and other information. Absolute encoders have multiple detectors and multiple unique tracks. The disc produces grey code output, a binary number system for which, unlike straight binary, successive values differ by 1 bit. So the maximum possible error, if the encoder stops between transitions, is half a bit. This position value is always available, even if the encoder shuts down. The number of slots on the disc directly affects the resolution. If there are too many lines, or slots, this will decrease the light that can pass through because the slots are smaller, and also the signal strength decreases as the speed increases. An optical encoder may have a mask installed between the detector and the disc, which increases accuracy by sharpening the edges of the light pulses falling on the detectors. The mask also allows for adjustment to discs of different resolutions, but can also increase cost, has a risk of interference, and allows less light to the detector. Optical encoders increasingly use no mask in favour of better technology in LEDs, detectors, and lenses to reduce phase error and increase edge detection. The code discs, or wheels, can be etched metal or plastic, emulsion on glass, or chrome on glass. Glass discs give high edge definition, are immune to condensation, and are durable, although they can be scratched and can fracture under shock. Plastic discs are shock resistant, but may warp at high temperatures. Metal discs can withstand shock, heat, and chemicals, but are not as accurate as glass varieties. Optical encoders need to be ruggedly sealed for operating in harsh environments. Sand, salt, and fine dust particles can enter the encoder body, blocking optical processes and reducing performance. Ambient temperature variations can also contribute to encoder failure rates. When encoders cool down, the pressure difference between the outside environment and housing interior can draw air into the encoder. Then, the encoder's housing temperature will drop and the contained humidity inside condenses, collecting dew on the code disc, printed circuit boards, and wiring, increasing the chance of failure. Magnetic encoders are inherently rugged and operate reliably under shock and vibration and high temperature. Magnetic debris ingress can degrade rotary magnetic encoder performance, but other contaminants do not. Therefore, rotary magnetic encoders are often used instead of optical encoders. Magnetized strips embedded in a rotating disc or wheel are sensed by either a Hall effect or magnetoresistive sensor. The motor speed and the position accuracy will dictate which of the two methods is better suited to an application. Some miniature magnetic encoders have a single magnetic pole and a small system on a chip design. The single north-south magnetic wheel passes over an ASIC, application-specific integrated circuit, which contains integrated Hall sensing elements and digital signal processing, which allows simultaneous incremental, absolute, and pulse width modulated digital outputs. For high-end encoders, higher resolution is expected than Hall effect sensors can deliver, and magnetoresistive sensors differ from Hall effect sensors in two important ways. The saturating field is much smaller, which makes magnetoresistive a much more sensitive measuring device, and the change in resistance is independent of the magnetic polarity. So a 32-pole wheel generates 32 pulses per revolution, twice the resolution of Hall effect sensors. Inductive encoders are position sensors which operate by tracking the current flow resistance relative to a nearby material in one or more coils. The signal processing circuitry can be located away from the measuring area, which allows use in harsh environments, but accurate inductive encoders can be large, heavy, or too expensive for mainstream applications. Often, encoder feedback is used to ensure that current is applied to motor windings when the rotor magnets are in the correct position to maximize torque. Suitable encoders should be chosen for the appropriate size, strength, and resolution. Resolution is the smallest physical movement measurable. For incremental encoders, resolution is defined as the number of counts per turn. Output is a square wave, and the number of pulses are known as pulses per revolution, PPR. For absolute encoders, each position of the shaft has a unique value specified in bits. The amount of bits is determined by how many rings or tracks are on the encoder disc. The first track has one transparent and one opaque segment. The second has 2 of each, the third has 4 of each, and so on. The number of tracks determines the absolute encoder's resolution. An encoder with 12 tracks is a 12-bit encoder, which has a resolution of 4096, or 2 to the power of 12, increments per revolution. The accuracy of the output will depend not only on the resolution of the encoder and the sampling time of the control system, but also on the condition of the equipment or system being monitored. Mechanical errors such as play in a lead screw, backlash in a gearbox, or the flexing of components will reduce the accuracy of the system, and installing a high accuracy encoder will not improve performance. If the accuracy required has a tolerance of plus or minus 2 millimeters and the position is always in a different place within this tolerance, then it is accurate but not repeatable. Repeatability is a mechanism's ability to return to the same position multiple times under identical conditions from either direction. For example, a device in your system can be described as being repeatable to plus or minus 10 microns. Just as a system can be accurate but not repeatable, it can also be repeatable but not accurate, as when a target moves repeatedly in the same place outside the tolerance. Mechanical factors most influence repeatability, but this can also be affected by system changes such as expansion and contraction due to temperature fluctuations. While accuracy can be compensated for by adjusting amplifiers and controllers, repeatability generally can't be. As an example, let's consider a football player. If the player is accurate, he's able to get the ball close to the goal when the situation occurs. If he is repeatable, he will shoot to this location every time possible. The best players are both accurate, hitting the goal, and repeatable, doing it every time. Most encoders mentioned here are supported by bearings which allow the shaft and disc to turn, while the encoder housing remains static. These bearings are not designed to support high loads, extreme shock, vibration, full system load, or misalignment. Bearing assemblies can be built which allow speeds up to 30,000 RPM. But if the encoder is hard mounted to the motor shaft, and the encoder housing is hard mounted to a base plate, the bearing assembly could be subjected to excessive side loads. Encoder mounting styles are typically classified as shafted, hollow shaft, hub shaft, and bearingless. The type of mounting chosen will optimize both the life and the performance of the encoder. Shafted encoders can be either flange mounted or foot mounted to a fixed surface, typically a bracket, and will have a flexible inline coupling to connect the encoder shaft to the motor shaft. A shafted encoder can also be driven by a belt. This is an option when the shaft is too large for the coupling or there is no space to mount it in line. These techniques also isolate the encoder from shock, vibration, and movement in the motor shaft and provide electrical isolation. This configuration is generally applied when a hollow or hub-shafted encoder is not available, when using a non-standard motor or the shaft movement is too extreme. The downside is that these techniques require more space and careful alignment, add more complexity, and can cost more. Hollow shaft encoders can be directly mounted on the shaft of the motor and fixed using a clamp. A flexible tether, or arms, attaches to the motor face or another fixed object to prevent the encoder body from rotating with the shaft. Direct mounting is also possible with hub-shafted encoders, except that the motor shaft does not extend through the encoder. The encoder is electrically isolated from the motor shaft current by using a plastic sleeve or insert between the motor and encoder shafts. Direct mounting has several advantages. It's easy to select for the correct shaft size and requires no alignment, and plastic inserts and flexible mountings to provide mechanical and electrical isolation. But the disadvantage is the flexible mounting will lead to measurement inaccuracy in high accuracy applications. A bearingless or ring encoder consists of a magnetic wheel mounted on the motor shaft. One or more sensors are mounted on the motor face and aligned with the sensor wheel. This arrangement eliminates the need for any couplings or bearings, as the motor itself provides this function. The bearingless encoder also takes up less space along the shaft of the motor, as they mount directly onto the face of the motor, although the quality of the signal is entirely dependent on the installer's ability to properly align the wheel of the encoder. Every different application will require a different encoder. The type of cable and number of connections will depend on the type of encoder. Incremental encoders will have a source and ground wire and a wire for each channel. One for single channel, A channel, two for quadrature design, A and B output, indexed quadrature designs, A, B, and Z channels that also provide communication abilities, U, V, and W channels. Incremental encoders can be connected using single wires or twisted pairs. For single-ended wiring, each channel requires only one wire, so a single channel encoder could use as little as 3 wires in the cable, voltage, ground, and channel A. An incremental encoder using twisted pair cable with an index and commutation feedback would require 8 connections. Voltage and ground, 1 connection for each channel A, B, and Z, and 1 each for commutation channels U, V, and W. All up, this is 14 wires, which means higher cost and opportunities for faults. Single-ended wiring is cheaper and quicker to install, but not very robust for long runs or in a noisy environment. Twisted pair connections can have cable runs up to 100 meters long and will cancel out any electrical noise, but the downside is they cost more and are double the number of wires per channel. An incremental encoder's output will be a series of voltage pulses. The quality and accuracy of these pulses will depend on the transmission distance, the type of encoder, and how the signal is being received. An encoder needs to be chosen with the correct output driver for the application. An encoder output driver amplifies and processes the raw signal into square wave signals, which will be transmitted onto another device or drive. There are three types of output for incremental encoders. A line driver output has become the standard output, particularly in a high noise environment or long cable runs. A line driver can actively force the output high and low, which enables it to sync and source current from the load. Longer cable runs require more current and may appear as current spikes to the line driver, which responds by dropping the voltage. This distorts the square wave signal, so an encoder line driver must be chosen with sufficient current capability. The open collector output is a simple and cheap option for low-end devices. The transistor acts like a switch, with the collector input left floating or open. A pull-up resistor is used to pull the signal down and switches the signal on and off to generate a square wave signal. This is generally used with single-ended wiring with cable runs less than a few meters. The push-pull line driver is suitable for high noise applications and works well up to 10 meters. It is typically used for incremental encoders with single-ended wiring for A, B, and Z signals. Absolute encoders can be wired in parallel, which make all the outputs available at the same time. Absolute encoders output a multi-bit digital word, which will be unique for each position. To interpret this multi-bit word, both the encoder and the receiving device need to speak a common language determined by the drive protocol. The drive control architecture will typically determine the communication protocol used. An alternative to parallel communications is serial. There are several standard serial buses available, as well as the standard industrial networks. SSI encoders offer an all-digital point-to-point serial arrangement with speeds up to 1.5 MHz. BISS is a similar open-source serial communication used with absolute encoders. Typically, this arrangement has 2 wires for power, 2 for clock, and 2 wires for data. Point-to-point serial protocols require 1 slave per master, while industrial buses allow multiple devices to be connected to one master. Addressing can be set using Rotary or dip switches, or by software, and if the device is located at the end of the segment, an integrated terminating resistor can be activated. Common bus protocols include DeviceNet and Profibus. For many bus networks, the encoder supplies absolute position only when interrogated by the controller. The bus may be configured to send data only on startup or on change of state. These methods cut down on bus traffic, but demanding a position update may take a few milliseconds. This may be a limiting factor if high accuracy is required. The majority of signal transmission problems will involve electrical noise, with the problem increasing the greater the distance that is covered. Using proper shielded cables and proper earthing is important. Many problems can be avoided with good wiring and installation practices. Maintain continuity of wires and shields from the device to the controller, avoiding the use of terminals in a junction box. Keep power and signal lines in separate conduits. Radiated noise from nearby relays, transformers, etc. may cause undesired signal pulses on the line. Encoders also require regulated power to within plus or minus 5%, or operation will be affected. The encoder case must be grounded to ensure proper and reliable operation. Some encoders have provisions for a case ground connection through the connector or cable if a ground cannot be secured through the mounting bracket or machine ground. Use high-quality shielded wire and connect the shield only at the instrument end. Also, an encoder using twisted pair shielded cable ensures that wire-induced currents will self-cancel. In industrial environments, high current fluxes are created by motors, motor control switches, and magnetic fields. This can result in varying electrical potentials at different ground points. To avoid problems, ground the shield together with all other parts of the system requiring grounding from a single point at the instrument end. Summary. The two most common types of rotary encoder are incremental and absolute. Incremental encoders will indicate the position only as the position changes. Absolute encoders can indicate the position without movement. Rotary optical encoders consist of an LED light source, a light detector, and a code disk. The disk has rotating transparent segments to interrupt the light beam. The number of light pulses indicates the position change. The resolution of an incremental encoder is defined as the number of pulses per revolution. The resolution of an absolute encoder increases with the number of tracks on the disk. A 12-bit encoder has 12 tracks, which will give 4,096 positions per revolution. Rotary magnetic encoders have magnetic poles embedded on the disk. The number of pole changes indicate the position, and they can be incremental or absolute. Encoder mounting styles are typically classified as shafted, hollow shaft, hub shaft, and bearingless. The type of mounting chosen will optimize both the life and the performance of the encoder. Each channel may only require one wire, so a single channel encoder could use as little as 3 wires in the cable, or as many as 14 for added functionality. The majority of signal transmission problems will involve electrical noise. Using proper shielded cables and earthing is important. Many problems can be avoided with good wiring and installation practices.